Alice could intercept this message X, she's not at all at the blue location, and store it for a little while, and then send it back to the verifier 0. And so from verifier 0's point of view, they're actually, the message could have come from the blue point. And likewise, Bob can intercept the Y, store it for a little while, and send it back. And now, from the verifier's point of view, everything looks hunky-dory. There seems to be someone at the blue position, but actually there isn't, right? Because this clearly Alice and Bob have faked that. So this doesn't work. So let's try to make it a slightly more complicated. And let's send an X and a Y to the prover, who then, upon receiving both these items, has to do some computation on them, some function, f of x, y, which results in A and B, and then A and B have to be returned all in due time so that it could have arisen from the blue location. Now let's see how this could be broken, and it can be broken, because Alice could do the following. Upon receiving X, she just copies it, stores the first message, and sends the copy on to Bob. And as you can see, Bob can do exactly the same thing. And now at this point in time, you see that Alice has both X and Y, and so she can compute A. And Bob also has X and Y, and he can compute B. And so they can send it on and sort of still fake or spoof this protocol. And so actually this is showing that in the classical world, there cannot be a secure position verification protocol, because you can always somehow do something like this, no matter what protocol you think of. Okay, so classically, there's nothing interesting to be done. So it makes sense to actually look at another way of looking at the attack. And so we're now sort of changing our mindset to be the attackers, Alice and Bob. And so Alice and Bob receive an input X and Y. Without loss of generality, they can send a message to each other. In this case, it's classical, so they can send it, and they have to output A and B. And in this case, without loss of generality, in the classical case, we can assume that the message is X, and the message that Bob sends is Y. But note that this reasoning wouldn't be valid in the quantum world anymore, because you can't copy your input. If your input is quantum, you couldn't play this anymore. So this opens up the possibility of having quantum protocols for this. And so this is the first inversion I'm thinking of. So we now change our mindset from making an honest protocol to thinking about attacks. And so what could be a good quantum protocol? And here's one where the verifier 0 sends a random qubit to the prover, and verifier 1 sends a random bit. And the prover, upon receiving these, sends to the verifier, if B is 1, he routes on the qubit to verifier 1, and if B is 0, he returns the qubit to verifier 0. So this is a very simple protocol, and it actually feels quite secure. At least the previous attack doesn't work, right? Because you can't copy psi and then sort of send it on and keep it. So this seems like a reasonably secure protocol. So let's look at the attacking game for Alice and Bob. And so without loss of generality, you may assume that Bob sends on his classical information. And it actually kind of feel almost that there is a cloning going on here, because if B is 1, so from the message that Alice sent, Bob has to be able to recover psi, right? So if B equals 1, the message MA needs to contain psi. On the other hand, if B is 0, Alice has to be able to recover psi from whatever she has left at home upon receiving psi, right? So upon receiving psi, she made 2 messages, one that she sent on to Bob and one that she kept to herself. And whenever B is 0, she has to be able to recover psi from that message. So it seems that now if you look at this and stare at it, it seems that Alice and Bob can clone psi. But, and actually in the paper, Chandran et al. Thought that they had a secure quantum protocol in this case. But it turns out that this is not true, because when you have entanglement, you can actually do this protocol. And the idea is to use teleportation, which I guess all of you know. It's a way of sending a qubit using an EPR pair and a measurement and 2 classical bits, so that if Alice sends these 2 classical bits to Bob, then Bob can recover from his half of the EPR pair. He can recover the original state psi back again. Right, so I guess you're all familiar with how this works. So here's how you can break the attack of the previous case. What Alice does is she teleports psi to Bob. They use 2 EPR pairs. So Bob receives this encrypted version of psi. And now when B is 1, he just keeps that. And when B is 0, he teleports it back. And this all goes instantaneously, right? I mean, there's no timing in this. This all happens in no time. And then what they do, they send to each other. Alice sends these corrections C1 and C2 to Bob, and Bob sends back D1 and D2 plus B to Alice, right? This is all classical information, so they can also make a copy and keep it to themselves. And now notice that if B is 1, remember that Bob kept his half of the EPR pair. He didn't teleport it back. And so from C1 and C2, he can recover psi, as you see here. So from C1 and C2, Bob can change psi tilde to psi. On the other hand, if B1 was 0, then Alice can, she has this psi double tilde, which is now doubly encrypted. And from the message she got from Bob, this D1, D2, she can change psi into psi tilde. And from the message C1, C2 that she made a copy of herself, she can change it into psi. And so this is a way of breaking that protocol that we just looked at. So with entanglement, you can do it. And then, of course, the game was on for more complicated schemes that would be secure. And quite a few of these schemes were put forward. And then, actually, we showed that there is a general no-go theorem, that none of these schemes are secure. And in general, you can always break a quantum protocol. But we needed actually a double exponential amount of entanglement of qubits to do this. And then later on, Beige and Koenig came with a very elegant proof that only required an exponential, but nevertheless an exponential amount of qubits. So that's how it stands now. So any position verification protocol can be broken with an exponential number of qubits, but the best lower bound is linear. So the question is there a better lower bound than linear, or is this exponential upper bound sort of the optimal thing? And this is a huge gap between the two. So this is very interesting. So in particular, does there exist a protocol for which the attack requires a lot of EPR pairs, but the honest prover and verifier are efficient? So this is actually something that I believe is the case. And this would be very interesting because this gives you actually in practice a secure position verification protocol using quantum. And then question 2 is, can you realize these protocols in an experimental, reasonable way? And also that we have been looking at, but I won't be talking about that because it's complicated also because you have to deal then with imperfections and errors, photon loss and actual speed of light, etc. But I'm focusing on question 1 here. By the way, how much time do I still have? Because started a bit late, I think. How much? 3? 2? 20? 20 minutes? No. Yeah? Oh, that's good. Very good. So I'm going to focus a little bit on question 1 here. And to my surprise, I'm a computer scientist, this actually had interesting relationships with complexity theory, with classical complexity theory, but also with classical cryptography, as well as with string theory, you will see, and even functional analysis. And so apparently this is a deep question that somehow pertains to many different areas, and I think that makes it extremely interesting. So let's look at a protocol that was suggested by Kent, Munro, and Spiller, and that somehow harbors all of the ingredients that you've seen so far. So here's how it goes. We have under the hood, we have a function, a Boolean function it's called, that